So one of the things I said a while back when we were talking about derivatives, is that one of the most popular applications of calculus, and in fact, the application for which Sir Isaac Newton actually went to the trouble of inventing calculus, is talking about physics. I don't know if I convinced any of you to take Miss Minter's calculus class this semester, but once again, you can check your plan of study and see if you've got any physics in your future in order to get the major that you want to have. But one of the things we talked about there is that there is this close relationship between motion and its derivatives. The derivative of motion is equal to velocity, right, with respect to time. Think about it. If I'm traveling 5 miles, I could say that my velocity is some rate. How do you measure the speed of your car? Well, you measure it in miles per hour. So that is a rate, that is the change in distance with respect to time. And in the same way that velocity is the derivative of motion, we have that acceleration is the derivative of velocity. The acceleration talks about how fast your velocity is changing over time, whether you're accelerating, which means that your velocity is increasing with respect to time, or if you're decelerating, if you're putting on the brake, which means your velocity is decreasing with respect to time. All right. So we've got that relationship between position, I guess is the fancy word for it, position and velocity and acceleration. And now that we're talking about antiderivatives and integrals, it's going to go in the opposite way. So just like we say that velocity is the derivative of position, we can say that position is the antiderivative of velocity, and velocity is the antiderivative of acceleration. Now that we've got those ideas, why don't we see some word problems where we're dealing with these very common ideas of what we call rectilinear motion in physics, and how we can solve those using a little bit of calculus. All right, so these are the kind of ways these problems get set up, and be used to seeing them because, as I say, this is a very common application problem in calculus. A particle moves along the x-axis, which means it's just moving to the left and right. It's moving along a normal number line, and its velocity is v of t is equal to 1 over the square root of t for t equals 0. So it starts when time is equal to 0 and just moves around. And a positive velocity means that it's moving up the number line. A negative velocity would be moving it down the velocity line. At the time when t equals 1, its position is 4. All right, so the first question here says, what is the acceleration of the particle when t is equal to 9? Okay, so the first thing I want to do is, why don't I change this into exponential notation? So think about what that would be. Notice we're using the square root of t quite a lot in these problems. So the square root would be 1/2, and it's the denominator. So I'm going to say that that's equal to t to the negative 1/2. All right, we want to know the acceleration when t is equal to 9. So what's the relationship between acceleration and velocity? Well, acceleration is the change in velocity over time. So that I need to take the derivative of velocity to get acceleration. So acceleration in time is equal to v prime of t. And so the derivative of v prime, so now I'm doing the derivative in the way that we're used to. So it's negative 1/2 times t to the negative 3/2 power. Okay, so that's the acceleration at any time. What if I want to find it just when t is equal to 9? Well, all I need to do is substitute 9 into this equation. So a of 9 is equal to, I should be careful because my a's do look like 9s, don't they? So it's negative 1/2 times 9 to the negative 3/2 power. When things get this weird, I don't want to do this in my head. I want to make sure I'm using my calculator. So I'm going to write this as negative 0.5 times 9. And I want to use the x to the y power. So -9 raised to the power of -3/2. I'm going to write that as -1.5. And press equals, and the calculator will do all the thinking for me. So that is quite a lot there. All right, so I'm going to write that down. So that's around equal to -0.0185. I don't know how many digits to write there. Okay, so that is just calculating the acceleration just by taking the derivative of the function with respect to time. Okay, and I am very quickly just checking my work there. Yep. So if I were using this with the functions, it would actually be, that would turn out to be -1/54 if you were doing the variables carefully, which honestly, I really should have done. Okay. So let's answer the second question here. What is the position of the particle when t is equal to 9? All right. So we know about velocity, now we know about acceleration. What's the relation of position to these things? Think back to what we said earlier. Well, velocity is the derivative of position, which means that position is the antiderivative of velocity. So in order to find the function for position, normally we write that as x of t. So I will once again write v of t is equal to t to the -1/2 power. And so the position of t, which normally we write as x of t, because we're using x as our function because it's the location on the x-axis, right? Particle moves along the x-axis. So we use x as the variable, or as the function name for that generally. So I want to take the antiderivative of this function. So we're going to take our variable, we're going to add 1 to the exponent, so that becomes 1/2. And we want to divide by 1/2, which is the same as multiplying by 2. So that's going to be 2 times t to the 1/2. We're taking the antiderivative, so we have to add our constant term. And how can we figure out what our constant term is in this case? We've got this fact here that at time equals 1, the position is 4. So 4, so I could write that as x of 1 is equal to 2 times the square root of 1 plus c. X of 1 is equal to 4. 2 times the square root of 2 is 2 plus c. So c is equal to 2. So we've got that x of t is equal to, substituting it back into this equation, I can write that as 2 times the square root of t plus 2. But we want to know the position of the particle when time is equal to 9. So that equals 2 times the square root of 9 plus 2. Square root of 9 is 3, so that's 2 times 3 plus 2, which is 6 plus 2, which is equal to 8. All right, so the basic idea that we have here is that it's moving around, and at time equals 9, so 9 units of time after we start, the particle is over here at 8 on the number line, and notice that its acceleration is negative, which means that either it's going this way and slowing down, or it's going this way and speeding up. How could we figure out which? If we wanted to, and the problem doesn't ask us to do this, obviously, we could calculate the velocity. So the velocity after 9 units of time is 1 over the square root of 9, which is equal to 1/3. All right, so at 9 units of time after we start, the position is over here at 8 on the number line. Its velocity is positive, which means it's going this way. It's moving to the right, but it's slowing down because the acceleration is negative. So it's got the brakes on, but it's still moving in this direction. Okay, that was a little bit more than the problem asked us to do, but the idea there is that we can solve problems about velocity, acceleration, and position and relate them to each other when they ask us questions like this. So, as I say, this is going to be a very common real world application that we're going to be asked about quite a lot as we continue to practice our integrals and derivatives. So, tie that back into physics.